Hello, everybody. I'm Seb, and today I'm going to be talking about my hobby, which is making music with FPGAs. I gave a similar talk last year, but I promise there is some new stuff. So if you see some things that you've already seen, please don't be disappointed. But I want to start by giving you a bit of a glamour shot. So this is a Tiliqua module and a screen. These are both kind of hardware gadgets that I designed in a Eurorack system. And so what Eurorack is it's the most popular, I guess, hardware format for building your own hardware synthesizers. Lots of sound designers and producers have systems like this, and that's kind of the reason I decided to go in this direction. But what I want to talk about today is the Tiliqua project, which is kind of two things. On one hand, it is a hardware platform, like a reference platform, open hardware, that you can very easily load different bit streams onto, test them out, has all the audio stuff in there, has USB streaming, all these other functions that are nice for audio stuff. But another important aspect is that the Tiliqua project is quite a large library of audio DSP cores that you can reuse. So even without the Tiliqua module or the Tiliqua hardware, you could easily take the DSP library. It has quite an audio focus and use it on other FPGAs or other technologies, whatever you want to do. And kind of one of the interesting things about the Tiliqua hardware is that it's designed to be easy to share, like bit streams, packaged bit streams with other people. So when you turn it on, you get a screen like this, and I can basically upload up to 8 different bit streams on here, and then I can just pick one, and it will reconfigure the hardware, reconfigure itself to be something else. So now I have an 8-voice polyphonic synthesizer. It gives me a little bit of a description about what's going on here, what all the different jacks do. I can switch to the visualization mode, and now when I touch it, it shows you some graphics. I don't have audio here, unfortunately, so you can't hear it, but you can maybe imagine what it sounds like. You know, I have some... this is kind of a polyphonic sawtooth waveform going through some reverb and some effects and stuff like this. And then if I hold down the encoder, I can go back to where I was before, and then pick something else. Maybe I want, this is a custom CPU that does some DSP stuff, and it's running some firmware. So this is a very different architecture. The previous one we just looked at is actually all gateware DSP. This is all software DSP with a big fat RISC-V CPU. And so this is selecting different things that the core is doing. That just gives you a picture. But kind of one of the goals with this project is that it should be useful to musicians as well as engineers, like without actually touching the HDL at all. And so what the module has is a bunch of audio inputs and outputs. They're touch sensitive, has a video output, it does USB audio streaming, has some expansion ports and MIDI. Looking a bit closer, the heart of the whole thing is this system on module, #SOM, which has an ECP5 FPGA on there. Kind of the idea is if you develop on this platform, then you can easily take the module and integrate it into something else if you want to. These were quite annoying to design. But now I'm going to talk about, how do you actually program this thing? So all of the DSP stuff in this project is written in Amaranth HDL. Well, actually, the entire project is written in Amaranth HDL, except for the CPU, which is VEX2. So that's spinal HDL, but literally everything else is Amaranth HDL. The way that it works is there's a whole bunch of different components, and you can quite easily hook them up together using something called Amaranth Streams. That's just kind of a valid, ready handshake. You've probably seen something like this before. And all of the DSP cores have a very similar interface, and you can trivially connect them together in Python using an interface like this. There's also, some more complicated stuff in there, like sharing DSP tiles and stuff like this. That could be a whole talk in itself, how that works under the hood, but I won't go into that today. I wanted to go through what's happened in the last year. We have frequency domain processing. So there's lots of FFTs, there's Cortex, there's windowing functions, STFTs, which is used for like frequency domain processing of time domain signals. So you can make things like vocoding effects and stuff like this. I'm also I'm kind of pushing with a lot of help from the Amaranth community on the fixed point extensions to the Amaranth language. And that's sitting behind a lot of these new DSP cores which have been added. and I found at this conference there wasn't much Amaranth on the screen, so here's some Amaranth. Here is the implementation of an FFT. You can see there's some, here's the twiddle memory being initialized with the basic Python math library. Here's where I'm testing the FFT against NumPy directly, so you kind of, with Amaranth and its simulation engine and with the fixed point extensions, you can natively do multipliers, complex multipliers, you have complex number types and so on, all natively in the language, and you can simulate it against, SciPy and NumPy, and then this simulation test bench, which tests a bunch of different excitations, is 100 lines of code. 100 lines of code. So yeah, just to give you an idea. Yeah, so other new things, there is like new streaming and visualization features. So here is a bit of a demo of using the Tiliqua in a system as a bridge between the analog and digital worlds. So on the left you have a simulated Eurorack system on a computer, and on the right you have some analog modules, and then the Tiliqua is acting as a USB audio bridge between the two worlds and visualizing it on the screen at the same time. So yeah, you can use it kind of as this is a simple example of a USB audio bridge, but you can also take DSP cores and kind of throw them in the signal chain between the analog signals and the USB streams, wherever you want to put them. So that's a new thing. Annoying thing, I discovered that the cheap MIDI keyboards that you buy often don't actually have MIDI, they just have USB. So of course I got nerd-sniped and decided to write a USB 2 host controller that just works with MIDI. That's purely in gateware. So if you're interested in that, the code is, of course, the code for everything here is up. Builds on the fantastic Luna framework from Great Scott Gadgets. I think that's the first USB 2 high-speed host core that I've seen around. Maybe there's another one, but I wasn't able to find anything else. And yeah, here's a quick demo of that. Okay. Okay, without audio, it's really anticlimactic, unfortunately. But this is a keyboard plugged into the Tiliqua, running USB 2 host stack, and then that's controlling a polyphonic synthesizer on there. Okay, great. Yeah, this is another interesting thing. So because the Tiliqua, like the module and the screen, are separate things, and because I wanted people to be able to share bit streams, one challenge is, not everybody has the same screen. Some people have screens of different sizes. You might have this little screen here. You might have a big screen, whatever. It's quite common that people have different screens, obviously. But if you want to share the same bit stream, then that kind of means that the bit stream has to, dynamically read from the display, okay, what timings do you support, restart the core, resize the frame buffer, do all this kind of thing. So that was quite a lot of work getting that running. So if you're interested to see an implementation of dynamic frame buffer resizing with an external PLL that gets reprogrammed when different screens are plugged in, then maybe this will interest you as well. And one other thing that I was working on is persistent options. So this is also kind of a, so now I'm sitting in the I'm sitting in this core here, so I can change okay, now I want to have this vector mode. Maybe I want change the color palette or something. Sorry, for some reason there's a lot of lag between the interface and the capture card, so it's really difficult for me to do anything. Yeah, so okay, interesting shape, right? Okay, now it's just like this. Now I can save, right? And then this is actually serializing it with right leveling to the local config flash of the FPGA. And now if I actually cut power, I'm just completely pull power up completely, and then plug it back in, it will remember, okay, I was in slot 1, and then it will boot that bit stream automatically, and then it will come up in exactly the same spot that you were before. And that sounds kind of trivial, but it was really difficult to do. And one of the reasons that's important is because if you have a live system where you have a huge rack and it's patched in a particular way, you really want to come back to where you were before if you power cycle everything. So yeah, that's that. Tiny GPU. Yeah. So I also wrote a tiny little acceleration backend for embedded graphics, which is one of the more popular drawing libraries for embedded Rust. And that means that actually the size of the CPU required for these DSP cores is even smaller because you no longer have to use huge caches to buffer like line drawing operations and stuff like this. So this is just a quick little demo of hardware accelerated drawing from Rust through like a command queue and stuff like this. So this is all, again, written in Amaranth as well. And yeah, I just wanted to finish up with some thank yous. So Tiliqua is now an LNet supported project, so I wanted to thank them a lot for their support. If you have a cool idea for an open source project, definitely go through the grant process. It's super easy, and I can only recommend working with them. I ran a crowdfunding campaign for this a few months ago and was super stoked that people actually wanted this thing. So thank you to everyone who backed it. I've already started putting them together. They're not quite ready to ship yet. Thank you to all these projects that were super important to this project. And thank you guys for listening. Yeah.
Thank you. Question, Olaf.
Have you had any time to actually make any music with this thing?
Yes. But I don't have a SoundCloud or something. But that's actually a super good point. It's really easy to get lost in the details of a project like this, and it's important to sometimes step back and just think, okay, why am I here at all? How did I get here? I don't want to build a CPU. I want to make music. Like.
You don't have to tell Olaf, I think.
I think it's a really cool project. Why did you choose Amaranth and not some other high-level HDL?
Yeah, that's a good point. There are a few reasons, I guess. I think so one of actually the big reasons was that I heavily use this Luna USB framework. So Luna is this gateware framework for building USB 2 high-speed cores that's written in Amaranth, and that allows that's a really important piece of infrastructure behind like the USB streaming and USB host stuff that you see here. But I guess another important aspect is I really like that Amaranth follows Rust's RFC process. I really like, at least for me, I found the syntax of Amaranth quite natural and easy to understand. And at a high level, when you're composing things like DSP cores together, I found that it's not scary for people that haven't had exposure to HDLs before to see this and understand what's going on. And for a project like this, where maybe musicians are also trying to create a custom DSP pipeline or something, then it's important to have something that's approachable. Yeah.
Okay, really cool project, but there are so many bells and whistles. What's your personal favorite application of Tiliqua?
That's a good question. So I really enjoy this kind of oscillographics type stuff that you've probably seen a lot already, like making interesting kind of shapes based on different sounds. I think for me the most interesting application is for different types of effects. And when I say different types of effects, imagine you have like a shimmer reverb or some kind of reverb effect that uses external memory, and then you start to overclock the external memory. What happens if you start to create artificial timing violations on the bus, or do really weird glitchy stuff like this? I think this is where the kinds of sounds that you might be able to create become novel and less like. Yeah, novel's maybe a good word for it, but like where you start to enter the realm of, okay, this wasn't possible before. This is kind of a bit weird. Yeah.
Okay, let's thank Sebastian again.